Hello there, my name is Mr. Evangelista, and welcome to another episode of Evangelista Science. In this episode, we're going to be talking about 4-2 of the IB Chem SL curriculum, talking about covalent bonds. Now, last week we talked about ionic bonds, which was a metal and a non-metal, where the metal loses an electron to the non-metal, thereby forming a positive cation and a negative anion, and therefore the positive and negative are electrostatically attracted to each other, forming an ionic bond. And this is all in hopes of becoming like the cool kids who are talking about noble gases, which should be right here. The noble gases, the cool kids. Now, sometimes not everybody can go in this kind of deal, such as an ionic bond, and they do what's called a covalent bond. So what's happening? So let's take a look at chlorine. Chlorine has 7 electrons. Now let's say there were 2 chlorine atoms, and they both each had 7 electrons. They're both trying to get to 8. Now, if one were to lose the electron and donate it completely to the other chlorine, the second chlorine would be happy, but the first chlorine would not be happy. And so this is what they do. They say, look, we're both trying to be cool kids. So why don't we share, where sometimes you can have my electron and sometimes I will take your electron. That way sometimes at least we'll be cool some of the times. And so they're going to share their electrons. And throughout this chapter, we're going to talk about something called the Octet Rule. That's just saying that 8 electrons or noble gas configuration is a stable arrangement. So here's that conversation that we were talking about between 2 chlorine molecules, and this is what happens with the Brinkelhoff elements. They each need 1 more electron, and they say, look, why don't we share electrons so that sometimes you're cool, sometimes I'm cool. So this electron that they're sharing is going to be spending time around, sometimes around this chlorine and sometimes around this chlorine. And what it does is it chemically bonds them together. Now oxygen needs 2 more electrons each to get to noble gas configuration. So they're going to do a double bond where they share 2 pairs of electrons. And nitrogen, since it needs 3 more electrons, is going to share 3 pairs of electrons, forming a triple bond. A couple of things on the strength of these bonds that we're talking about. So as we go down the periodic table, we can see that the bond dissociation energy here is the strength it's going to take to destroy this bond. We can see that as we go lower down the table, the strength that it's going to take to destroy this bond is going to get lower and lower and lower. Oh, you mean another trend to memorize? Well, hopefully you won't have to memorize this if you know this concept. So as you go down the table, the electrons are getting further and further apart. And since these electrons are further apart, it's going to be easier to break this bond here. So hopefully you remember that. Now fluorine's a little weird because Mr. E said going down the table was going to decrease bond dissociation energy. And then you might be asking, why is fluorine so low? Well, that's because the fluorine molecule is so small that since the electrons are like so close together, it actually gets in the way of this bond, and that's why the bond dissociation energy is so small there. Oh, that makes sense. Thank you, Mr. E. You're welcome. Okay, and talking about the strength of the single and double and the triple bond, the single bond is going to be the weakest bond, the double bond is going to be stronger, and the triple bond is going to be even stronger than that. Notice it is important to know that the double bond is not doubly as strong as the single bond. It is stronger, but it is not twice as strong. And, in continuation, the triple bond is not 3 times as strong as the single bond. It is stronger, but not doubly or triply as strong. Okay, so talking about what we've been going over the past 2 videos. With ionic bonds, it is a complete transfer of electrons. And this happens with electronegativities about greater than 1.8. So if the electronegativity difference between the 2 atoms are greater than 1.8, you're going to form an ionic bond. Now, sometimes we've been talking, all of these previous examples, we've been talking about molecules that are going to share evenly because they have the same electronegativity or the same attraction for electrons in a covalent bond. And so this is kind of what we've been seeing, where they kind of Sometimes the electrons will be over here, and sometimes the electrons will be over here, and for the most part, they're sharing that electron equally. What if we have some, for example, hydrofluoric acid right here? Fluorine is really electronegative, and hydrogen is not as electronegative. So fluorine is going to want those electrons more. So fluorine goes to hydrogen and goes, yeah, all right, we'll share. Share. And, hydrogen agrees. But what actually happens is that the electron spends a lot of time around fluorine and not a lot of time around hydrogen. So it's probably spending a lot of time here on fluorine, then fluorine's like, all right, I'll share. But then the rest of the time it's around fluorine again. We call this a polar covalent bond. Polar because we have these poles forming where this side is becoming partially positive and this side is becoming partially negative because this negative electron is spending a lot of time here. And that's opposed to a pure covalent bond where the electron is being shared equally. Now, it is hard to denote what electronegativity difference would lead to a covalent bond between a polar covalent bond and ionic bond. And so it is, when you're doing these descriptions for the IB, it is incorrect for you to say ionic or polar covalent or pure covalent. To be safe, make sure to use words like, oh, this compound would be very, very strongly covalent or predominantly covalent, or this would be predominantly ionic, rather than flat out and saying it's purely ionic or purely covalent, because again, the borders between those two isn't really strongly defined. So you need to use words like predominantly to kind of stay safe in terms of the IB. Now, this man right here is a master of chemistry, a hero in the world of chemistry. This is Gilbert Newton Lewis, and he is responsible for the Lewis structures that we are going to be talking about. He's an awesome dude. He was nominated for the Nobel Prize like over 30 times, even though he never won it. And, he unfortunately died working with cyanide. We don't know if it was an accident or if it was poisoning, but unfortunately he did die. But at least he died doing what he loved, which was working with chemistry. And so the Lewis structures, which was invented by him over 100 years ago, and we still use it today, it has its, limitations, but it is important in helping us kind of visualize these molecular structures. And so the Lewis structure, what it does is it takes a compound or a molecule and it counts the number of valence electrons and it tells us how the bonds and where these electrons are in this Lewis structure. And so we're going to go ahead and hop into some problems.
Okay, so let's draw the Lewis structure for SO2. So first thing to do is to count the number of valence electrons in your compound. So sulfur is going to have 6, and each oxygen also brings 6 valence electrons, so that's a total of 18 valence electrons. Now, when we're drawing these, you always want to pick the central atom to be the atom that it is the least electronegative, so the furthest away from chlorine. So that would be sulfur, and the other atoms will go on the outside of your molecule. And then from here, I would like to draw single bonds from the outer atoms into the central atom. What this does is I'm trying to get to 18 valence electrons in my structure here. And those single bonds each use 2 electrons. They are a pair of electrons that are being shared. So that's 1, 2, that's 4 electrons already out, and I need to get to 18. Now each of these, I work on the outer atoms first, and then I make sure that their octets are filled, meaning they each have 8 electrons. So I already have 2 here, so I need 6 more on this oxygen, and same thing for this oxygen. 2 here and 6 here, so that's 8 for octet fills for each of those oxygens. What does that put me at in terms of valence electrons? I'm at 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So now I worry about the central atom. I need to make sure the octet for the central atom is filled. And so I have 2 more electrons that I can put in to reach my 18. However, I have not filled the octet for that central atom. And so the strategy now is to start to use double and triple bonds to fulfill the octet. And what we're going to do is we're going to take 2 electrons from this oxygen to do a double bond here. And that way, this oxygen has 8. the sulfur has 1, 2, 3, 4, 5, 6, 7, 8, and this oxygen also has 8. Now, as a good chemist, as a good scientist, you should be able to see, well, couldn't I have just taken these 2 electrons from this oxygen, and therefore, wouldn't this structure be correct as well? Could you draw either one of these? And the answer is yes. What this is called is you represent it by double-sided arrows. What this is called is resonance. Okay, what does this mean? Does this mean that sometimes the structure is like this and then sometimes the structure is like this? No. Your book explains it a pretty good way, and what it says is when you're trying to explain the concept of a mule to somebody, you say it is an intermediate between a horse and a donkey. You don't say half of the time it's a horse and half of the time it's a donkey. It's actually somewhere in between the horse and a donkey, and that's exactly what is happening here with this structure. The actual molecular structure of sulfur dioxide is somewhere in between these 2 structures. Okay, let's take a look at another example. And this is going to be carbon monoxide, CO. So we don't have to worry about a central atom here because there are only 2 atoms, so there's no such thing as kind of like a central atom. But carbon is going to bring with it 4 valence electrons, and oxygen is going to bring with it 6 valence electrons. Okay? Now, how am I going to do this? So, I need to, so this is a total of 10 valence electrons, 4 here and 6 here, 10 valence electrons. So they can form a bond here and share those 2 electrons. Now this electron and this electron, we can form a bond here like that. So get rid of those. And then I can move this electron over here. Just move it like there. But our octets aren't filled. Okay, and so what oxygen is going to want to do is it's going to want to use these electrons to form a triple bond here. Okay, now the fact that these electrons, right, came from just 1 atom, we call this a coordinate covalent bond. And all that means is the electrons come from 1 atom. So the electrons from this bond came from the oxygen. A lot of times what you will see is the atoms will come into agreement. One atom will say, I will give 1 electron, you will give 1 electron, and we will share those 2 electrons in a pair. This is not what happened here. This is oxygen donating these 2 electrons to create a coordinate covalent bond. Kind of like what happened here in sulfur dioxide, where we had one of these oxygens donating the 2 electrons to create a coordinate covalent bond. That is a term that you will need to know for the IB. Let's talk about some exceptions to the octet rule. Now, IB isn't going to ask this, but for a lot of your college classes, there are a lot of exceptions to the octet rule. For example, sulfur can have up to 12 electrons around it. Now, we won't get too much into it. Just know that, if we're talking about a compound and it has more than 8 electrons, don't be like, well, Mr. Reed, you said that there could only be 8 electrons. I know I said that. But there are exceptions to the octet rule that are going to make it possible for there to be more than 8 electrons around certain atoms. Okay, and sulfur is one of those that can fit up to 12. So don't freak out if you see that. Okay, but the notable exceptions that IB talks about are beryllium, and the other one is going to be boron. Beryllium and boron are weird in the fact that they are happy not being in an octet. So if we draw the Lewis dot structure for beryllium chloride here, this is what it looks like. And again, you might be like, but Mr. E, there's no 8 electrons around the middle BE. I know that. I understand that, but BE is just one of those weird exceptions where we cannot have a full octet, and we consider this the actual molecular structure. Same thing with boron. If I'm going to draw it here, it's going to look something like this. Again, I understand that it's not a complete octet, that there are only 6 electrons around this boron, but you just have to accept the fact that there are exceptions to the octet rule.